Okay, so here we also can have loading effect by the equipment we are using to make the measurements. So we have to make sure that whenever we are making measurements, we are using the appropriate equipment. Yes, right in college, in the labs, you are exposed to very inexpensive equipment, one size fits all. So, but that's not how the industry works. When you are designing something, you are going to have $5,000, $7,000 multimeters that is going to be making very precise measurements, that is going to be calibrated in the way that it does not affect or change the dynamics of the circuits, much less the readings that you need to make from the circuits. So here it is, a regular voltmeter saying, making the measurements. We have R1 and R2. They both are 470, okay? So we assume they are the same value, so the 10 volts should split evenly. So I should read 5 volts here and 5 volts there. But instead, the multimeter or the voltmeter right here is measuring 4.04 and 4.04. So I'm losing 2 volts, and that it has to be done with the fact that the ohm meter, we assume when we make calculations, we assume that the voltmeter has an infinite resistance. But infinite, we don't, infinite to us is a huge value, okay? That's what infinite means. A big value that when we connect it in parallel to here is not going to change the value. We assume that this 470 is at least 10 times higher than the value, smaller I mean, than the value of this internal resistance of the voltmeter. But a 470 kilo ohm is a pretty big value. So that means that this has to be 10 times higher than that. The internal resistance of the voltmeter has to be 10 times higher than that. Your standard $150, $200 voltmeter has a maximum internal resistance of 1 mega. So if you have 1 mega in here, that's not 10 times bigger than 470. So that's why we see this loading effect happening here, okay? So let's see what it says here. Assume Vs is 10 volts, but the meter reads only 4 volts when it's across either R1 or R2. Can you explain what is happening? Yes, right here. All measurements affected the quantity being measured. A voltmeter has internal resistance, which can be changed the resistance of the circuit under test. In this case, a 1 mega. Yeah, this is pretty standard. Your regular $25 to $150 voltmeter internal resistance is going to be a 1 mega ohm of the accounts for the reading. So that's what is happening. We are experiencing here loading effect. So you see, even not having the right equipment to make the measurements can affect the design. Let's continue. Okay, the wheatstone bridge, it's a very, very famous configuration, widely used both in mechanics and sensor design, because the way it is connected, it is very sensitive to any changes. So any minor changes can create a voltage difference between these 2 points, and therefore a current, and that can be measured, amplified, and therefore it can become very sensitive, very useful for very sensitive calibration equipment. So that's why this wheatstone bridge is very popular. You have to learn how to solve it. You have to learn how to Theveninize it. You have to learn different rules that govern this design. It's just that you have to, as an electrical engineer, as an electrical technician, you have to know how this configuration works. So we are going to spend some time analyzing this configuration. So let's see what it says. The wheatstone bridge consists of a DC voltage source and 4 resistive arms forming 2 voltage dividers. The output is taken between the dividers. So we take the output, it just becomes a differential voltage. So this point minus that point give us the output. That's basically what it's saying. The output is taken between the dividers. Frequently, one of the bridge resistors is adjustable. Yes, that becomes our sensor. The sensor that we are designing, the sensor that we are reading. The bridge is balanced. We also going to be introduced to the fact that when we say the bridge becomes balanced, what does it mean? That the reading in here, the output voltage is 0. That means this point and that point are at the same potential. Doesn't mean it is at 0. It just means that if it is 5 here and I have 5 here, 5 minus 5 is 0. So the bridge is considered to be balanced because my output is 0. Very different than saying that the voltage at this point is 0. The differential voltage is 0, which means this and that are at the same potential level. Very important to keep in mind, okay? The bridge is balanced, the output voltage is 0. And the products of resistance in the opposite diagonal arms are equal. Yes. So this is a characteristics of what this makes this design so important. We are saying that the product of the opposite diagonals are equal. It is important because we are going to use those relationships to solve for unknowns. Okay? So here is our example. There's solve this circuit. It says, what is the value of R2 if the bridge is balanced? So they are telling us that this point and that point are at the same potential. So the difference between the two is 0. That's what it means by it says the bridge is balanced. And they give us the answer right here, but I worked it out, so let's go over this. So we have the bridge, we have our source, we have our R1, R3. We want to know what is R2. We have R4, and we know that the B out is equals to 0. So what is R2 if the bridge is balanced? The bridge condition is B out is equals to 0. If B out is equals to 0, that means B1 and B1 and B3 are the same as the same ratio as B2 and B4, because that's what would put us the potential right here. So B1 over B3 is the same, B1 over B3 is the same as B2 over B4. Or we can put it in resistor values, like the statement was saying, that R1 over R3, the ratio of these two resistors, is equal to the ratio of R2 over R4. Okay? So from here, if it's balanced, these conditions stand. So I'm just going to solve for R2. So R2 is just R1 over R3 multiplied by R4. So I get 385 kilo ohms. So that is the value of my resistor that will make the bridge to be balanced. Remember, doesn't mean that all the resistors have to be the same. It has to be the combination or the ratio of R1 over R3 and R2 over R4. In other words, the odds and the evens have to be the same ratio for the bridge to be balanced. So let's stop right here, because the other example is going to take more time. So let's stop.